Hello, my name is Andrei Avrubov and I will represent you modeling surfactants by dissipative molecular dynamic technique. What is the dissipative molecular dynamics? Such models are used when we need to study the behavior of the system containing very many molecules for a very long time. That's why it's called dynamics. The dissipative particle dynamics method was introduced by Hoberg and Kuhleman with these requirements for the model. It exhibits hydrodynamic behavior. It has thermal fluctuation that can drive Brownian motion. It's cheap to simulate. Now dissipative particle dynamics method involves considering the interactions of groups of atoms rather than individual atoms. In this method, these groups of atoms called beds and specific characteristics are assigned to them to represent their behavior in real environments. For example, let's consider the structure of a surfactant. Here you can see sodium lauryl sulfate in water. If we were to analyze the interactions between all atoms within the molecule, we would certainly determine the molecule's behavior. However, when dealing with the interactions of even a few molecules, many accurate methods become time-consuming and resource-intensive. DPD is applied when it's necessary to calculate interactions involving a large number of atoms, as you know, such as the behavior of colloidal system. Surfactants in water are the colloidal system. So to perform calculation using the DPD method, you need to prepare the initial input files. It include the file for your surfactant for water and the initial input file for a program that has commands for the program what to do with your initial components. In this method, sodium lauryl sulfate, for instance, is represented as a collection of spherical particles, so-called beds. It doesn't matter from which end we consider our molecule, but in our case, we will start with the hydrophilic group, an orange sphere. In the DPD method, the thread this group as a single particle. After identifying all the hydrophilic group, in our case, there is only one. We move on to the hydrophobic tail, which breaks into segments in such a way that the overall structure of resulting model corresponds to the real existing molecule. I made this section by eye, but I believe it's possible to conduct a real experiment to obtain data on the micelle formation and adjust the number of beds we use to represent the hydrophilic tail accordingly. In this way, we reduce the interactions of 42 atoms in the molecule to interaction involving only 5 effective particles. 4 types of atom, carbon, oxygen, sulfur, and hydrogen, are represented by just 2 effective beds, hydrophobic and hydrophilic. By making this assumption, we significantly simplify the calculation of the molecular dynamics. Solvent molecules, in our case water, are treated in a similar manner. So here you can see how the program file, initial program file, looks like. Here we can see name of our surfactants, sodium lauryl sulfate. Here the number of pairs that involved in our molecule. A type of pairs, it's just for program. One means that it's hydrophilic, and two means it's hydrophobic. Number of bonds in our lauryl sulfate, it's bonds between the particles, so it's 1, 2, 3, 4. 4 bonds, and the order of bonds, so one connected with the second atom is connected to the third one with the third with the fifth. And here the length of the bonds. So here you can see that water is just a single bed with the type of bond number 3. So the dissipation or the description of the dissipation particle dynamics technique. Basic algorithm total force on the particle is contained three types of forces. First one, conservative force acting between particles. It's similar than other dynamics, molecular dynamics technique, and other two makes our molecular dynamic technique dissipative. So FD, dissipative force, corresponds to the friction force. There is here you can see a formula for this, and Rij is the difference between atoms coordinates, and Vig is the difference between velocities of these atoms, and gamma is a important coefficient controlling the strength on the friction force between DPD particles, and omega d describes the variation of the friction coefficient with the distance. And the third one is the random force, determine the magnitude of the random pair force between the DPD particles. And here the formula for the random force. And what's important that dissipative and random coefficients depend on each other by these equations. These basic formulas allow us to determine the behavior of the colloidal systems. Here you can see the parameters for the input file. This file is used to modeling not like initial components, but it shows the program, the way how these initial files interact with each other. So the main parameters here, for my opinion, is box size. Box size is affect to the density. In our case, we use box size 20 20 20. It's correspond to the density 3, and if we will increase the box size, we increase the density. And what's important not for program working, but for us to observe. Here you can see 100. It means how much time we can see the program will save frame for us. With this frame, we can model in our system, which you will see later. And this number is how many iterations will the program do before it will end. So here you can see it's this interactions section is also in this input file, but lower. We can change parameters here, like here the smallest parameters that I tried for the lauryl sulfate, and here you see the modeling of this system. It's how the particles are, its particle behavior in the solution. So you see this, like we hardly can see anything, but if we will increase the parameters, these parameters, by the way, corresponds to these forces, like conservative force. It shows the acting between atoms, and it also shows, like all forces in general, it shows us how what strength we put to the other systems that force atom to organize colloidal particles. Like in the first one, we see that there is no micelles or something else. But if we will increase the parameters, we see that this like quite a big micelles. But what's interesting then, if we will increase the parameters in 5 times, the size of the micelles decreasing. So I also tried with a different concentration. By the way, here was concentration like 6 volume percent, and here like 6 volume percent is like the same diff. And with the 12%, we can get with the same parameters, interaction parameters, the bigger micelles that kind of look like a big long rope than than a micelle. So, and on 18%, we can see that the all micelles come to the one age, and they kind of form a different phase. And what's important that it's a lot of time, it's errors. Like here I showed a few examples of error that I got. So actually I first start with the black screen, like there was nothing, there was only one particles that working on the screen, and I don't know what was the cause of this. I just to play with the parameters, and then I found this. This usually happens then we in the input pile for our surfactant we changed the type of bond for water. Like 3 we used for water, and water is not showing on the model, so we don't see anything. That's why it happened. So I think that's all. Yes, thank you for your attention.